Okay, hi everyone. My name is Jesse Kanter. This is intended for the 208 physics lab for section CC4 for spring 2015. Hi guys, this is basically instructions for what to do with your data from the lab electric potential and electric field that we recently did. So I'm just going to go through showing you how to make the different plots, especially I know the one in the electric field we'll get to at the end that people might have trouble with. So what I have here, we can look back at the setup of the experiment. Remember we had something that looked like this, and you had an inner cylinder with radius RA and an outer one with RB, and we measured along the radius every 5 millimeters from RA to RB what the voltage was. And what I do in this Excel sheet now is, this is every 5 millimeters, so 5, 10, 15, whatever. And then, as you can see here, this 4.8 divided by 2 was that diameter of that inner cylinder divided by 2, so that's the radius. And then plus these made in millimeters, and then this 1,000 converts that into meters. So now I have the radial distance, and I have the three voltages, columns of voltages that I measured for the different radii. And what we're going to do now is, you can already see I named this V average because we're going to take the average of these values. So what I'm going to do for that is just equals. Now you could insert, C2 plus C3 up to plus D2 plus E2 divided by 3, or to be a little quicker, it already gives you average. You just do parentheses, click on this one, comma, and voila, it gives you an average. Now, of course, the nice thing about Excel is that once you do this computation once, you just drag this down. You have to click that little square you see on the right bottom corner and pull it down all the way. And now it does that for every line you see. So now we have our V average, and we're going to plot. The first thing we were asked to do was plot that against the radius. So we'll go ahead and do that. We took too many points, so we're just going to try it again. Okay. So now we have our plot. This is our V average, and this is our radius. I do want you to obviously, put labels on these as well. A label with V average in volts and radius, and if you convert to meters like I did, meters. If not centimeter, just whatever the appropriate units are. I'm not going to go through that now because I kind of want to get through this lab and do the things I think you might not be familiar with. But as you have been putting labels on before, keep doing that. So anyway, now that I have this, we expect this to follow a log, meaning that the voltage should vary as log of R. And so what we'll do is we'll add a tread line. So we right click and we go to add tread line. And right now it has a linear one, so I'm going to switch to logarithmic. And when I go to options, I want to display the equation on the chart for this the tread line that it's trying to fit my data with. And I want to display what's called the R-squared value. The R-squared value gives me an idea of how good my fit is. I'm going to click OK now. Move this over here. And that R-squared value is always between 0 and 1. 1 would be perfect, and 0 would be, absolutely horrible. So here the R-squared is 0.96, which is good. Something the best is when you see like 0.99 or more nines, whatever. But this is decent. In my case, actually, I can show you that if you plot this and try to do that again with that tread line, logarithmic, options, you get an even better fit, which you can even see looking at the graph. The reason for this, I'll just tell you, so going into this, is when I took the voltages here, unlike you guys who had a whole 2 hours to do this lab, I had a whole 20 minutes maybe, and so these weren't taken as well because it was kind of rushed. So we might come back to just doing V1 when I want to show you something that's a little more precise and show it working, but for now we'll stick with the V averages because that's what I want you guys to do in your lab. So now okay, again, this is just, as you can see by clicking on it, it's v average versus this radius, and we plotted, and we made a fit. We can also do is we can add an uncertainty. So for here, with the uncertainty that I would use, because your voltmeter actually should be pretty precise, is the following. I would say between these three values, take the maximum one and the minimum one, and the difference between them divided by 2 should be your error here. So the way I would do that, you could go through each one, and here I would say it's 2.36 is the maximum one and 2.05. That's kind of annoying. What I would do is Excel has a way of finding a maximum from a list. You would just write max and put these numbers in, minus, you guessed it, min. And again. You can already see I made a mistake with the max. Is that plus, plus, plus? That's not going to make sense to it. It needs to be commas. That's actually just the difference. We wanted to find that divided by 2, so I'm just going to put parentheses around here. Divide by 2. And the reason I want to do that instead of looking for each one is because now I can just pull this down, and now I have all of them. So now you have these errors, and you want to create error bars on here. So what you would do is you go back to this graph, click on the data so you have them lined up, and you go to chart layout, and you see error bars. The error bars are like standard error percentage. Those would do things based off of just, you know, where the data is in relation to each other. We actually want to give specific values, so what we do is error bar options and custom and specify a value. So then you're going to click on this little, you know, weird looking thing over here, which I don't have a great name for right now, but and you would drag down over here to tell them that these are the sets of data you want to use for your error. So that's for the positive error value, meaning it's going to be on top of your data point, and below your data point, we just want the same amount of error. So same thing. You know, be sure it's in this form here. I'll just scroll through it, but I'm already messing things up that way. So I'll go back here and draw this again. Yeah, if you have like something, this plus something, it's going to be kind of wrong. So just, you know, fiddle with this. You can just follow exactly what I did. You press this, you scroll down over these. I'll do it one more time. Press that. I would erase whatever is here, and then press and scroll. Okay. So now, and we'll say OK. It's the weird thing with them that they don't let you know exactly where horizontal and vertical are, but I find that if you do this and then you don't want I'm not putting horizontal error bars in this, so if I press on them and then backspace to delete, so now we just have the vertical ones. And you can see that, you know, seeing most of these were pretty small in comparison to here. You can almost not see them, but you can see a few of them. I'm just going to enlarge this so you see error bars here, and that actually does help us a bit because, you know, this data point itself isn't as close to the line as we want, but it seems like it's within error. And it actually seems like we have a pretty good fit if we take into account our error. So that was just, you know, applying the voltage against the radius. So now what I'll do is I'll make a different plot where they want you to plot it now against log of r. So now instead of using a log fit, we'll be able to use a linear fit. So what I'll do is this is equal to log. When Excel just says log, it means natural log, which is the one you're going to want to use here. And I'll insert this value. Okay. And now I'm just going to copy these because I just want that again. I'm going to copy. And now when you paste here, you have to actually paste special and do values. If you don't, it's going to take the same way this averaged the previous 3 columns. This will average these 3 columns, which is not what we want. So that's why you have to paste values. And just to make things clear, this is my L and R. takes to be the trademark R. It should not. We'll do R space. Okay. So now I'm just going to plot these. And now what I can do is when I add this tread line, I'm actually just going to use the linear fit because now it's the voltage over against log R, and we expect it to depend on log R, so it should only be some constant times it, so it's a linear relationship. And again, I want to see my display equation, display R value. You can actually see it's the same R squared because it's really related plots. So actually in the future, you know, like when you're writing the lab report, to be honest, you could not put this graph in and put this one in as long as you explain, you know, instead of plotting against R, you can just say, you know, we plotted the voltage against log of R and we did or did not see a linear relationship. And I'll just add my error bars again here real quick. Chart layout, error bars, error bar options, custom, specify value, top and 4 minus. And again, I don't want the horizontal ones. And you can see now again, this linear plot is falling in between, more in between the errors when we take them into account. So that's actually all for the potential. And as I said, you can work mostly with this graph in your report if you want, as long as you explain, you know, this is voltage versus log plot. So I'm going to put these over here for now. So now comes the part where I think everyone's actually going to have a little bit of trouble, so I'm just going to explain this. Now, as the main point, is how to calculate the electric field, because the electric field, we want to basically take a derivative of this voltage here with respect to the radius. So for that, I'm going to go back to my original plot, which was just voltage versus radius, and make the following observation. If you look closely at this, if we were to draw a line between this point and this point, then we can sort of get the slope in between them. And you can think of it this way. As you go through a curve, although the slope of the tangent, which is, you know, the derivative, is changing as you go through R, over a small change in radius, the change in the slope is almost that of a line, meaning this is obviously not a line, it's a curve. But you know, from this point, let's say, to here, is more like a line. It can be approximated as one. And so for that reason, we can take the distance, you know, the sort of tangent between these lines and say that's the tangent derivative here, and then do the same between these two and between these two, and that way we can we can find a set of data which will actually be our derivative. You know, obviously that'll be more fine-tuned if you actually had more points. So if instead of doing 5 millimeters, if we had done every 3 millimeters, that would make this better and better. So, you know, obviously it's a question of efficiency, how much time you have to take how much data. But just to give you an idea that the reason I'm saying this, that the more points would be better accuracy, is because it's just to drive home that idea that the reason this works as an approximation is because as you get to a smaller and smaller difference in your R value, or, you know, if this is a Y versus X value, the more and more that's just going to be almost approximated well as a straight line from point to point, and then you can just find the slope. So now I'll do that in action. So I'm going to actually start with the second point because, and you'll see why. So I'm going to do equals my Y value, which is the V average, minus the previous Y value. I actually want to put these in parentheses. Divided by my R value minus the previous one. And again, I need these in parentheses. And you know this as how to find, you know, the slope of a straight line between 2 points. The Y values of the second one minus the first one over the X value of the second one minus the first one. That's just the slope of a line between 2 points. So what you're doing really is this tells you the slope of the line between this voltage and this voltage over R. So now I'm going to drag this down, and I'm doing that every step of the way. Here, this is the slope between, this voltage and that voltage over this radius and this radius. And if I plot this now as a function of r, something got a little messed up here. I'm actually going to insert. No. Well, basically, what I wanted to do is go over here. I'm going to just do this again. Equals. These are just the same numbers as you can see, and I'll show you why I want to do this. Is because here I want to put 1 over r, because we expect the electric field to be as a function of 1 over r. And so I can just plot these two together. And what I should get is a graph that shows this y values, which is my electric field now, or some term proportional to the electric field, over r, or 1 over r actually, sorry. And so this should really be a linear plot. We can see it's not so perfectly, but I'm going to add a tread line and see how well it can be approximated by 1. Not so great, 0.7 for our r squared value. For me, I think in this case it was because, as I said, these were taken rather quickly. If I change this to, instead of using that average value, I'm going to use my V1s, and the graph will do it for me. Much better, right? This point is off, but okay, it's not perfect, but it's still a lot better, and we're at 0.92 now. And I can consider this slope, this is, so some constant times x, which is now, x is now 1 over r. Keep in mind, it's not r, it's 1 over r. That's what I plotted this against. And since we're seeing a linear relationship, that shows us that our electric field does depend as have the 1 over r dependence, and we can find whatever other terms are in the expression for electric field through this constant. And that's the basic idea. Again, remember, you need the symbols and units, which I didn't do here. Your averages, I expect, will work better for you because you took the time to do this meticulously, or at least I hope you did. But again, just for that electric field, keep in mind the way you do it is, again, you find the slope of line between points where it's just, now we're working with this, is basically this point minus that one divided by this point minus that one is the slope of the line between this set of points and this set of points. And you do that for each of them. That gives you a derivative, and then since you expect this to be a 1 over r dependence, you plot it against 1 over r. As you can see, 1 over r's, and that will give you the electric field as a function of against 1 over r graph. And we found what seems to be roughly a linear relationship. For error bars on this, what I would do, and we'll end with this, is I would take the error you got here, and I would do the following. First, I would do the value I got times the error of this point, which was 0.08 divided by this value. This is something that should be in your lab manual of how to do these types of error calculations. I'm just doing it really quickly, but it's something you should be familiar with. And probably oh, yes, I need to tell it. Multiply, please. And something is definitely wrong. Yep. So we want F3. So now that was basically just adding the errors from these two in terms of percentage of the average. These were a certain error and they were a certain percentage. The final result of my addition or subtraction multiplied by the addition of those percentages in terms of error. So now I could go here, do one more time, error bars, error bar options, custom, specify value, drag over these, drag over these. And again, there weren't huge errors, but it does, this point and this point, weren't on that line, but now with the error bars, it seems like they could be within it. For some reason, the point was still off, but okay. You can discuss different possible error analysis besides the error values we took and say, how could I didn't take into account anything for the radius here. That's another place error could come from. And you should talk about what errors you had in those sorts of measurements. But here I think I gave you the basic idea of how to make these plots and mainly how to find that electric field by, again, the slope of the line between different points. All right, I hope this was informative, and if you have any questions, again, remember you can ask me on Tuesday after class. I'll be around for an hour, and I'll be happy to take any questions, and I'll have my computer there and can show you anything that wasn't clear here. All right, thanks for listening. See you guys later. Bye.